we are starting our first day on our unit for thermochemistry. One of the first things that I do want to look at here is the difference between temperature and heat. And you do not have this on your notes, but I think it's worth us noting because this unit is going to be about heat energy among some other things. But it's worth our knowing the difference between temperature and heat. So if I were writing this down, I would probably jot it down either at the top or maybe down at the bottom below that little chart that you've got there. You've got some room to be able to write that down. So the first thing that we want to look at is temperature, and I would also abbreviate. We are only talking about kinetic energy. If you talk about temperature, it's referring only to kinetic energy. Whereas when we talk about heat, that's going to be energy of both kinetic and potential. So kinetic energy plus potential energy. That's going to be one of the big differences. If we look at the definition of temperature, the definition is the average KE, average kinetic energy, of all particles. So the average kinetic energy of the particles. Average kinetic energy of the particles. Whereas heat is going to be, if we look at the definition or we think about that, we see that heat is going to be transferred from higher temperatures, higher T, to lower temperatures, lower T. So it's showing us a direction of that energy, how it's moving. And then finally, we've got some units in there that they're measured at. So we know that temperature is measured in degrees Fahrenheit, degrees Celsius, or Kelvin, but we're going to see that heat is energy, so it's measured in joules. All right, so now you've also got on your paper an example of a heating curve. I would not write all of this stuff down. You've got enough stuff to add to it, so I personally would not add what we're going to talk about to my heating curve on my paper. But make sure that you understand if you've got something, and actually I should first mention the way this heating curve is set up. You've got temperature on your y-axis, and then you've got heat added on your x-axis. So if we're talking about a phase of a substance that exists at really, really low temperatures, what phase is that going to be? Low temperatures. Solid. And then you can see it gets to liquid and then gas as we move up. So gases have higher energy. And then what if here for B, for example, we're seeing all you have is one temperature. There is not a change in temperature, but it's not a solid and it's not a liquid. Well, what that means is you've got both of those phases that exist at that point. You've got those phases in equilibrium. You're producing solids and producing liquids at the same point. Same with our point D up here. It's our liquid and gas phases are both existing there. And then, of course, we know the term, if you're going from a solid to a liquid, we know that means melting. If you're going the opposite direction, that's freezing. So you should be familiar with those terms, but I don't know that that's worth writing down on your paper. But you should be familiar with all of that. So then that takes us to, I'm going to skip that, a formula that you have. I'm going to go back to your heating curve later on, and we're going to talk about it some more, but right underneath it, you have some formulas that are written. More on the left-hand side, you have this formula, Q equals mc delta T. So what I would do right maybe above that, this is really important, that you use that formula when there is one phase with a temperature change. One phase with a temperature change. So I would find a way to write that up there. Right above Q equals mc delta T, one phase with a temperature change. And then we can look at what these variables stand for. So you've got a place to write this down. Q is going to be your energy, and it's going to be energy as heat. M, what do you think would have more heat energy? What do you think M stands for? Let me ask you that first. It is mass, because what would have more heat energy? A teacup of boiling water or a swimming pool of boiling water? The swimming pool, because it's got more mass to it. So M stands for mass, C stands for specific heat, and delta T stands for your change in temperature. Again, I would abbreviate these things. Heat energy, joules. Mass, grams. Specific heat, joules per gram degrees Celsius. Delta T is your change in temperature. Whenever you have a change, it's always going to be final minus initial. So you should have that listed as well. Okay, so now when we go through and eventually work these problems, I'm not going to require that you set it up exactly the same way that we've done a lot of our dimensional analysis, but you still have to show your units, so really it is dimensional analysis. To show you how this works out, if I were to take this formula, Q equals mc delta T, we know that mass is measured in grams, and it's up to you if you want to write this down. I know that C, my specific heat, which I'll explain a little bit more thoroughly in a second, is in joules per gram degrees Celsius. And then my change in temperature is degrees Celsius. So you can see how all of that cancels out to give us our joules as our final answer for our Q. So the math works out. Okay, so now that we know what formula to use when you have one phase with a changing temperature, let's think about some of those variables. Specific heat was one variable that you guys are probably not too familiar with. I would write this down, specific heat, and it's measured as C. That's the variable that's used. I would just write down it's measure of the capacity of a substance to absorb heat. Measure of the capacity of a substance to absorb heat. Measure of the capacity of a substance to absorb heat. So before we even go into that further, let's pretend it's a hot sunny day here in Austin, Texas. Maybe it's 107 degrees outside. You've got the bright sun shining down, 107 degrees outside. Which one of these slides do you guys want to be on? With your bare little shorts, shorty shorts. Let's go with the plastic, because you get on this one and you'll be screaming because you're burning yourself on that metal slide. And the reason being, it has to do with the specific heat capacity. That we see the metal slide has a really low specific heat, whereas the plastic slide would have a much higher specific heat. So because the metal slide has a low specific heat, what that means is it doesn't have the capacity to retain that heat value. Instead, it changes dramatically. So when the sun comes out, it gets hot really quickly. When the sun goes away and it's cold out, it gets cold really quickly. Kind of like the desert. If we were to think about the desert, where you've got, I'm going to jump really quickly to here. You've got this on your sheet. We see that water has a really, if you compare that to some of the other common substances, you see that water has a really high specific heat value. So going back to our desert example, there's not much water in the desert. Instead, you've got a lot of stuff like, granite. You've got different rocks in the desert and very dry air, not much water. So what that means is during the daytime, it gets really, really, really hot. But at night, it gets really, really, really cold because it doesn't have the ability to retain, hold on to that heat value. Whereas if you were to go to someplace like maybe the coast of California, where you've got all this water around, all of the ocean right there, it's very moderate. You've got nice mild days and nice mild nights. And that has to do with this high specific heat value. If we go back to what another part of this definition, it says it's defined as the amount of heat energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Well, that makes sense. According to our units, it's the heat energy required to raise 1 gram by 1 degree Celsius. So that's where those units come in. You can just think about what the additional part of that definition is. Okay, I'm going to keep going now. All right, that was when you have a temperature change, but you're just working within one phase. We also have some formulas that can be used with a temperature change, one temperature with a phase change. So I would take a second to write that down as well on top of these two formulas. Okay, and the variables that we're going to be using are pretty much the same. We've still got Q and M, those have not changed. But now what we're going to see is we've got something known as H sub V or H sub F. That is, oftentimes it's called the latent heat of fusion or latent heat of vaporization. And in both those cases, we measure it in units of joules per gram. So now if I were to come and try and show how that works in dimensional analysis using either one of these formulas, it really doesn't matter. I see that my Q, my joules, is going to equal my mass, which is grams, times my heat of fusion or my heat of vaporization, which is joules per gram. And we see that the units work out perfectly that way. And then I guess we should probably say something about these words right here, because we're about to see this on our heating curve, that whenever you think of the word fusing something together, what phase do you think of? Solid. So we're thinking about a solid here, whereas if you vaporize something, you think about a gas. Both of those are going to contain the phase of a liquid, but one also contains the phase of a solid, the other contains the phase of a gas. So now that takes us to your heating curve that you have on your paper, and we can see here, for example, we know that this is a solid, so that's one phase. If you have one phase, what formula might you use? Good. So MC delta T. One phase right here, MC delta T. One phase, MC delta T. And within that one phase for each of those things, you have a temperature change. So you've got some rise on that vertical axis. But now those other parts that I left blank, here, notice, and let's pretend, actually we're not pretending, it tells us that this is for water. So this is a heating curve for H2O. That means I know this value is 0. I know this value is 100 right here. So at this point, at 0 degrees, I can have a substance exist as ice. I can have H2O exist as ice or as water. So along this line, where I have a phase change, either going from ice to water or water to ice, I don't have a temperature change. It's still at 0 degrees. So what formula would you use here? Q equals MHF. It's that fusion. You've got that solid combined with your liquid. And then our last one over here is going to be in between your liquid and your gas. So it's going to be MHV. So those are going to be the formulas we use, and then the next thing that you just need to do is really be able to identify where you are on the heating curve, and then the math should all work out pretty well. Okay, so something else we want to make sure that we understand, and I would just throw this onto the heating curve that you guys have in front of you. You can either work in this direction, or you can work in this direction. In other words, you might have solid that turns to a liquid that turns to a gas. In that case, what's happening with energy? Are you gaining it or losing it? You're gaining it, right? It goes from a solid to a gas, let's say. So in that example, heat is, or energy is absorbed. How would you describe that? Endothermic. And then the other would be if you release, it's exothermic. So here's what I would write on my paper. I would say that if it's moving in this direction, that your that's going to be exo, and your delta H is going to be a negative value. We've seen this in many different ways over the past units. And then if it's moving in this direction, it is endothermic, and our delta H equals a positive value. So that's going to be important. Make sure you have that drawn on your heating curve. All right. Little something that we can say about our latent heats of fusion and latent heat of vaporization. If we were to see one of these actually scaled properly, if we were to see a heating curve scaled properly, you would see that this would be a tiny little line, and then right here we've got a much longer line. And the reason being, if we ask this question, which requires more energy? This part right here, where all you're doing is just loosening up these solids to turn to a liquid, or this part right here, where you're actually taking these molecules that are held together as a liquid, and they're overcoming these intermolecular forces and breaking apart and turning into a gas. This takes a lot more energy. And if you guys were to flip back and look at this, for example, you would see that 2260 compared to 335 takes a lot more energy to overcome those intermolecular forces and turn into a gas. Okay, which now takes us to the first example that we have. And here, you're going to notice what I did on these. These first few that we learned today, there's one that's a little bit more challenging. But the first few that we learned today, they're pretty simple as far as our heating curves go. They're just going to be small little segments on the heating curve. But when they get more complicated, it becomes a really good tool for us. So I want you guys to just do a tiny little sketch on each of these problems and think about what part of our heating curve we're considering. So the first example, it says how much heat energy is required to raise the temperature of 44 grams of lead from room temperature, in other words 21 degrees Celsius, to its melting point at 327 degrees Celsius. And it gives us the specific heat for lead. So we are starting at room temperature for lead. Is that a solid, liquid, or a gas? That's a solid. And we're raising it to its melting point. And, you know, my heating curve that I drew here, I didn't give myself much room on my solid line. But there is one point and one point only on this heating curve that I have that melting point being shown. Do you see where that would be? Can you visualize it? And hopefully you're saying right there. That is it. That's where we're trying to go to. That's that 327 for this situation. And we're starting somewhere lower than that. So this is all I need to see on your heating curve. That's what I want you guys to do, is just show that it's starting at a lower temperature as a solid and it's being heated up to its melting point. Doesn't say anything about actually making it turn into a liquid. We're just heating it up to its melting point. Reading through this problem again, do you guys know what formula to use? You've got three possibilities, and by the way, you do have to memorize all those three formulas. Which one is it going to be? MC delta T, and the reason being one phase with the temperature change. So Q equals MC delta T, and we just start plugging in. So we have 44 grams, and it's up to you guys. If you want to show this like this, fabulous. I didn't do that last class, but maybe I will this time. If you'd rather, actually, yeah, I'll do it that way this time. Just to show you, you guys have a couple options. If you rather just do it in parentheses and show the math, but I do need to see units on these. But you don't have to set it up like this. Our C, we're given that as 0.13 joules per gram degrees Celsius. And then we're going to also multiply that times our change in temperature. Remember, it's your final minus initial. So that's going to be our 327 minus 21, and that's degrees Celsius. So give you a second to plug that in. Okay, so we have an answer, and our answer is 1750. That should be in joules. Oh, here's a little note about sig figs. I hate sig figs. I hate this problem here because what we see is we actually have two sig figs there. Do you want to call that a constant and say that that doesn't limit you? Or do we want to just pretend, let's pretend this says 0.130, and there we go. There are our three sig figs. I'll try and make all of your quizzes and tests pretty straightforward on all of that and not be a big issue for you guys to figure out. Okay, so that is it. Let's also think again about our endo-exo dilemma. It's going in this direction, so therefore your delta H is what? Positive, which is what we came up with. The math made that work out because we had this number was positive for our change in temperature, so we expect that to be a positive value. Okay, next one, it says in a laboratory experiment, we have 58.1 grams of copper. It loses so many joules in cooling from this temperature to this temperature. Calculate the specific heat of copper. Well, if you're calculating the specific heat of something, you know that's going to be a positive number. There's no possibility that you could get a negative. Just like mass, you're not going to get a negative mass. If we look at our heating curve, it's going from 99.8 to 28.4 for copper. Oh, this is going to be hard to get this in here. It's going from a solid to a solid. I am not on that point. That's not at its melting point. It is just cooling is all it's doing. So it's a solid that is going from one point to another, but it doesn't ever change phases. There's nothing in here, even if you don't know anything about copper, there's nothing in here that suggests it's changing phases. So we're just going to move in that direction. Hopefully you guys are all saying, yeah, this is the formula I would use, because we see a change in temperature. It's not that flat line. It's not one temperature. You have a change in temperature. The way I would probably set this up is I would say, well, I'm looking for the specific heat of copper. I would probably just do this algebraically. I know I would do this algebraically and just change it around and say that this is going to equal Q divided by M delta T. So then you can just start plugging in. If you want to try and do this with the chart like we did on that last one, great. Or if you just want to plug it into problems, that's a great way to go. So your Q, excuse me, is 1.6 times 10 to the third joules. I'm going to come back and say something about that in a second. My mass, I see, is 58.1 grams. Notice I'm still writing all my units in there. And then my change in temperature is 28.4 minus 99.8 degrees Celsius. And on this one, this, by the way, happens to be negative 71.4 is what you get there. All right, any answers on that? 0 point. Okay, let's take it out one more. Even, no, 3.9 is perfect because of this guy. Where is it? There he is. I had 3.86 written, but really 3.39 is better. So just like we would expect, joules per gram degree Celsius is what we're left with. That's what we would expect to get our units for specific heat in. Now, what I want to bring up is the sign convention, and I'll get questions here in a second. It is going in this direction, which means our delta H is actually a negative value. It is totally up to you guys if you want to plug this in, but the best way to do this really is to plug that in as a negative value because it's going in this direction. It is cooling, so that implies that that's a negative value, even though you won't see the sign given to you in the problem for your joules. And then this is negative as well, so that's why your specific heat ends up being positive. If you went through this and you got your negative answer just like you probably did in your calculator, then you have to look at this and go, well, specific heat, it's always positive. It's not possible to get a negative value, just like mass. You wouldn't get a negative value for that. Okay, was there a question or good? Okay, next one. To what temperature will 117 grams of nickel be heated if it starts off at 18.3 degrees Celsius, absorbs this many joules, and we get our specific heat. So again, Q equals MC delta T. In this case, I am looking for what temperature. So I'm just going to say my change in temperature equals Q divided by MC. If I think about where I'm at on my heating curve, I'm going from I'm starting off at 18.3 degrees Celsius, and all I know is I'm increasing, I'm absorbing some heat energy. So I'm just going to do it to right there. I did not give myself much space, but again, that is not at the melting point. There's nothing in my problem that suggests that I go to the melting point. So as I start plugging in, I'm going to say 2.46 times 10 to the third, that's in joules, divided by my mass of 117 grams. And I'm also dividing it by my specific heat, which is given to me as 0.444 joules per gram degrees Celsius. Hopefully you guys can always all look at this and say, well, these grams cancel, joules cancel. You've got 1 over degrees Celsius, which flips up to the numerator, so you've got your answer in degrees Celsius, which you would expect. So I am going to be the calculator on these and just kind of keep going with this as everybody's plugging in. But we see that the answer that you would get here, 47.36, so let's say 47.4 degrees Celsius. I find this to be the easiest way to handle these. Whenever you're looking for change in temperature, I do it separately instead of trying to plug things in over here. So now what I would do is I know that my change in any variable is always going to be final minus initial. So that's going to be, actually let me say that if we're solving for, what are we solving for? We're solving for final. So that's going to be our change in temperature plus our initial temperature. So that's 47.4 plus 18.3, and we get 65.7 degrees Celsius. Okay, so every single problem, if you were to just skim back through those, you would see that they all have changes in temperature. But now we reach another one, and you guys just stop me if you have questions, because I'm trying to keep going here. All right, so we get to our next one, and here it just says calculate the energy required to melt 75 grams of ice if its heat of fusion is 335 joules per gram. So I think it's really a good idea, again, to show where this is on the heating curve, because this is where a lot of people have their little stumbling block. All we want to do is melt ice. So that's implying what phase are we starting at? Solid. And we want it to become liquid. But it doesn't give us a temperature of the ice. So what we have to assume is it's at its melting point. So there is one point for that. That is right here. We're taking ice and we are melting it. So I just took it and turned it to a liquid. That's all we're doing in this case. Again, there is no temperature change, but what we do see is a phase change from a solid to a liquid. So you know that you're going to use Q equals mH sub what? F, because you've got a solid involved. And of course it was easy enough because this was given to you, but lots of times on your homework or quiz or something like that, you might have to look it up on a chart. And in this case, we're going to say, and also we're thinking about this. Maybe you're thinking of it at the very end, but you're thinking about how that's going to be a positive value when you move in that direction. And we're just going to take our 75 grams and we're going to multiply it times our 335 joules per gram. You got to love the easy math on this. And that's all there is to it. I look and I see 3 sig figs. So I am going to round that to 25100 joules, and it is a positive value because it's endothermic. It's absorbing heat energy. Okay, a couple more. Next one, similar situation. We're just starting with so many kilojoules that are required to vaporize so many grams of a liquid. That's all it tells us, is we want to vaporize a liquid. So you're starting with it as a liquid, and we want to turn it to a gas. No temperatures are given. Only one possibility. Start with it here as a liquid, and you want to turn it to a gas. You want to make it do this. Again, you're thinking about how your delta H value equals a positive value. And we set it up. And this is going to be heat of vaporization. Okay, so this is our formula that we're using. We're going to change this around. It says calculate its heat of vaporization. So we actually want to solve for that value, which means it's going to be Q divided by M. I guess a place to make mistakes on these is if you're not confident with your algebra and changing variables around, you can make mistakes there. But If you write down your units and make sure the units cancel properly, that will catch you on that. So if you make an algebra mistake and you write down your units, you should be able to catch yourself on that mistake. Okay, so we have 86.1 kilojoules. This is a little bit different. It's given as kilojoules. And then we divide it by our mass, 58.2 grams. And it actually even asks for it as kilojoules per gram, so that's pretty easy. And in this case, it is going to be 1.48 kilojoules per gram. So if it did ask for it in joules per gram, you would just multiply times 1,000. Okay, we have done the simple little one-steppers. Now we get to my favorite problem, and we read through here. This is the last one also. And it says, calculate the energy that must be removed from 25 grams of water at 21 degrees Celsius as it is converted into ice at 11 degrees Celsius. So not only do we have a temperature change in there, we also have a phase change in there. Doesn't sound like we can do this in one step. So the important thing here is being able to identify where you're starting at and where you're ending at on your heating curve. So we know, actually I read through ice, water, I know my heating curve. This substance is H2O, so I can easily label these two parts right now with temperatures. That wasn't very meaningful to us in the other problems. We didn't need to do that. But right now, I can go ahead and label those. It's going to be meaningful if you're changing, if you've got multiple steps, you're going to need that. And then we see that we're starting off with water at 21 degrees Celsius. Well, this middle segment's my water, so I'm just going to say right in here somewhere, I've got 21 degrees Celsius. That is where we are starting at. And we want to convert it to ice at negative 11 degrees Celsius. Negative 11 is down here somewhere, so we want to take it down here. We are moving in this direction. So overall, what is our Q value going to be? Negative. This is going to be negative because of that. Also, how many steps do you think this is going to take us? 3. However many line segments you have, that's how many steps that you have on there. If I had a really big chart, maybe I would label this here as A, B, and C. I don't. I'm going to always move in the direction that it shows me that my question describes it as. So I'm just going to go ahead and label it over here. But my first step, and I know I minimized y'all's copy, so you might not have room to write all of this. It's up to you, but I'm going to write it on this problem. You don't have to put these words down there. I want to see the formulas, but what I'm going to write first in words is not important for you guys to do. But I'm starting right here. In other words, I am starting at with water at 21 degrees Celsius, and I want to change it to, what's that first step going to be? What am I going to do? Water at 0 degrees. That is my first step. Well, if that's what I'm doing in that first segment, going from water at 21 to water at 0, what formula am I going to use? Okay. All right, next step. I'm going to come back and plug in later. My next step. I've got it currently as water at 0 degrees Celsius. I am right here on my graph. Where do I want to take it? Ice at 0 degrees Celsius. Good. If I want to do that, what formula am I going to use? Perfect. MHF. So now, oops, let me get my colors straight. So now we're right there. Our last little step, we want to take it from ice at 0 degrees Celsius to ice at negative 11 degrees Celsius. Again, one phase with a temperature change, so that is going to be Q equals MC delta T. So now that we've got all that figured out, we know what we're doing on our heating curve. Let's go ahead and plug in some values. I am going to be efficient and know that my mass doesn't change. 25 grams, 25 grams, 25 grams. Now I'll continue with just A, just the first part. But I'm going to take it, my mass times my specific heat. Remember, this is dependent upon the phase. So for water, what do you come up with? Yeah, so you're looking at your specific heat for water, which is 4.184 joules per gram degree Celsius. It's going to get sloppy here. And then what about our change in temperature? What are you going to do here? And I'm going to probably correct you on it, but what's your gut feeling? What would you do? Yeah, so all you're doing, it's just that 21 degrees. So I know that people would say 0 minus 21, which is exactly the right thing because that's what we've been saying. However, make all of these values positive, and I'm going to write that after I write everything down. We're just going to deal with it at the very end. If you start getting positives and negatives in there, it will throw you. The reason I don't want you to make this negative is because we're not learning it to where this HF moving in one direction is positive and the other direction is negative. And that's really the way it works. So that's how this would then be a negative number. But we're not going to go there. So next one, we'll come back to that. We've got our MH sub F. So H sub F for H2O is what, 335 joules per gram? We'll come up with a value. And last one, we've got MC delta T. This is for our ice. So our C, specific heat of ice, what do you see? 2.03. You know, unfortunately, I need to change these notes. The chart that you have up at the top is different than the chart at the bottom. So I think one says 2.1 and the other says 2.03 for ice. Let's go with our 2.03, and that's in joules per gram degrees Celsius. And then our temperature change here would be what? 11. So I'm going to jot down the numbers that I've got. I just unplugged everything. Hopefully this is still working. Okay, so I'm going to jot down the numbers that I got here, and I got in my calculator was something like 2196.6 and 8375 and 55.825. Now what you're going to do with all these values is just take them and add them up. And when you add them up, let's round them to a whole number. So that's going to be our rule of thumb, is just round it to a whole number. So you get 11130 joules. And because of this right here, now I'm going to deal with my sign. So I know that that's the number of joules. Well, I'm releasing that much energy. So it's going to be, I don't know what I was writing here. Oh, that was an equal sign. Okay, so that's going to be equal to my negative 11130 joules. And I'm just going to deal with it at the end. It makes it so much easier. So a couple things that we said. Make this be a whole number. And then also we said, if you just make all of these things positive, then you're going to, that's the easiest way to handle things and deal with it at the very end. And that's all we've got.